Yes.
Great. So thank you to the speakers for those great talks. They were super interesting. And hopefully this half hour we can get some more answers and perhaps some more questions and perhaps some collaborations. So one thing that came to mind as I was listening to all those talks is that you could think of imitation learning as a type of offline RL, in the sense that you're getting a set of data, a batch of data from an expert, and you're trying to leverage this data to learn how to act near optimally, or at least close to the experts. And so one of the recurring themes that I felt kept coming up throughout the talks is this need to balance coverage of the, or this need to have coverage of the state and action space so that you can be certain of your estimates. And I was wondering your thoughts on how you balance this trade-off of more coverage versus sample efficiency. And by sample efficiency, I mean the amount of data you require in order to be able to do offline RL well, how this balance is handled in the offline RL literature versus in the imitation learning literature. I don't know, whoever wants to take the question. I wasn't directed at anyone in particular. I'd be interested in all of your opinions.
I believe Sergey's hand is raised.
So I can take a stab at it, although I might miss the point of your question a little bit, but let me give it a shot. So I think something lurking in that question is maybe a little bit of a difference in how the world looks when we imagine the problem as one where you have small data sets and small state spaces versus when you have enormous data sets with very diverse things going on. And I think in those cases, these things look a little different. So if you, even though mathematically they're very similar. So if you look at the world in terms of sort of small data sets and small state spaces, you might imagine, well, what we need to do is we need to see kind of what actions lead to which outcomes in kind of a good coverage of all the states that might happen. But if you think about it in terms of data sets on the scale of like, you know, basically all the rest of machine learning, like, you know, computer vision, NLP, and so on, then something that starts to come up is that you can't possibly see even a small sliver of everything, but what you can hope to do is you can hope to generalize. And you can hope to generalize not just in the sense of like, oh, I've seen like a very similar state, but you can hope to generalize across underlying factors of variation. And when that happens, then you can hope that your model will make sensible conclusions when it sees a mixture of factors of variation that it has never seen before, but where the individual values are similar to ones it's seen before. And that's generalization. And I think that once we start looking at the world this way, then it becomes much clearer where sort of where the power of the learning machine comes from. It comes from making these inferences and then deciding that, oh, because I've seen this thing over here and this thing over here, in this new state, this other action might lead to a good outcome, even though I've never seen that before. But we need to be in the mode of large data sets and generalization to actually, for that to make sense.
And maybe just to jump in on that. So I think another thing is that I tend to be a big optimist, like many of us, so, you know, optimism under uncertainty. And I think imitation learning, the best you can hope to do is to replicate the behavior in the data set. But ideally, and in our work and in a number of the other papers that have come out today, there's sort of safe policy improvement style guarantees, which say if you really don't have enough data to support any form of generalization, then you're going to revert back to a behavior policy. But the hope is that these type of offline approaches can yield, you know, performance that's even better, assuming you can either make these type of inferences and generalization that Sergey is talking about, and that you have sufficient support. And I think to me, that's the really exciting thing, is that we've seen so much benefit of imitation learning, but many cases we actually sort of within the data kind of have these latent better policies where you already have support, and either by stitching together or identifying successful trajectories, we can identify methods that will do even better.
So I don't know if Ophir or Tengu, if you want to add something, and if not, that's also fine.
Sorry, I didn't hear the question, so I guess I will skip. So like I was a bit late. I was just right back from teaching. There were a lot of questions after the class.
So okay, so maybe I'll go on to my next question. I think this tailed off well from some of the responses. So there is this issue of having state coverage, and there is this issue of being able to uncover these latent improved policies from what you're given from the data. And I'm wondering if given that a priori it's hard for us to know for generalization, like what type of coverage we need in order to be able to generalize well, or what type of examples we need to be able to find these latent policies. Is the answer to have more of an iterative process to offline RL, where you're given a batch of data, but then you're allowed to request more data and in a more specific way? So not just give me more data, but give me more data in these state action pairs. And Sergey, I think, alluded to this a little bit in his talk. And I'm wondering, because most of the results that have been presented have been in the setting where you're given the batch of data, and that's what you have to deal with. And I'm wondering how much can we get out of that if we don't know a priori what we're actually going to need without making relatively strong assumptions? And feel free, anyone, to jump in.
So I think it's a really interesting question. It came up this summer too at the Theory of RL workshop at ICML, and Shipra had some really interesting comments about how in some of her interactions with companies, they would ask her, how much better would the policy be if I could just get a little bit more data? Where should I gather that? I think in the bandit setting, where maybe you could target different demographics and it's easier to sort of teleport to the states you need, that might be particularly realistic. My personal thought is it depends on the domain, and so I'm curious to hear from others. I think it's something like robotics that seems pretty reasonable. In some other cases, like electronic medical record systems, I think it's a big ask to sort of do a lot of iterative updating, and so those scenarios, it may be much harder. It would be nicer to sort of see if one can have a significant improvement before collecting additional data before disturbing the workflow. So I'm curious to see in other domains, maybe I think in customer management, Amazon, et cetera, it seems a little bit more realistic in those scenarios. But I'm curious what Sergey and Tengu and Ophir think.
I think that there's kind of maybe a very pragmatic way to approach that, and then maybe a more conceptual way. So the very pragmatic way to approach it is, I suspect that as long as our algorithms are kind of imperfect and fallible, seemingly esoteric details of the data composition will continue to have a big effect. And it may even be less to do with, can I kind of get the perfect data, and more to do with certain very common data collection strategies could be pathologically bad. So let me give an example. Back when we were doing that QT-op thing that I mentioned in my talk, one of the things we found that was pathologically bad is if you just have a hand-designed policy that has no noise. If you have a hand-designed policy that's just a little too deterministic, it's just like really, really bad. And if you add even a little bit of noise, it becomes drastically less bad. And these kinds of little details are things that might be good to know, because if someone is going to go and collect a bunch of data using some baseline system, if that's an easy change to make, they might want to be aware of it. But that's kind of the pragmatic side. The more conceptual side, though, is that maybe echoing a little bit what Emma was getting at, is that in a lot of application domains, the reason that we want to do offline RL is because running online experiments is just really hard, either very dangerous or very expensive, or just in case of healthcare, you just like can't do it because it's like not legal. And in those settings, we really need to be able to get some baseline level of decent performance before we can hope to deploy anything at all. And maybe that baseline level of performance can be obtained with a sort of heavy behavioral cloning style regularization. So maybe if you stay close enough to the data, you can at least deploy something. That could be one way to go, but we have to be very conscious of that fact, because that's going to be a major limitation.
I guess I don't have much insight here, but I guess I have confusion. So every time I was thinking about this, offline plus online setting. So when you say you have some offline data and then you start with online exploration or online kind of like collecting data, so it just sounds like the best strategy is A plus B. You just say you do whatever the best you with offline, and then you start with that policy and do online RL. So and so far I haven't seen. Maybe it's just my ignorance, but I didn't see any method that can do better than this. So of course, this method is not that trivial to implement, because I think I've seen a few papers, in the past that try to do this, and then the problem is that what you initialize, right? Whether you want to initialize the policy from the offline RL learned policy, or you want to initialize everything. So and if you only initialize the policy, but your Q function is random, then probably it's not going to work, because your policy will be destroyed. Even your policy starting point policy, the initial policy is pretty reasonable, but the Q function will destroy the policy. And I think that's one of the reasons why some of this learning from demonstration approach didn't work very well. So, but I think suppose you somehow learn a good value function using some of the model-based approach we are doing, or some of the model-free approach that Sergey or Emma have been done. So, and you start with a good policy and good Q function, good model, so on and so forth, and you initialize all of them in the online R algorithm. I suspect that's probably the best you can do. At least, I'm not sure, but that's the best you can do. But that sounds like the best we knew how to do. So that make it a bit not very interesting. So yeah, that's my confusion, I guess. Yeah.
If I can jump into this one, I'm curious to hear that many of the talks that they talked about off-policy policy evaluation as an important inner loop, right, or something we need to do to address offline RL. Now, in online learning, there's also a tradition of being able to guarantee good performance without directly being able to evaluate, right, sort of hedge your bets type of approaches. And I think, Emma, you mentioned it in healthcare, for example, that we might just need evaluation. But I'm curious. Do we need are we looking under the lamplight by focusing on policy evaluation? Should we just look for completely different approaches?
And I think Sergey mentioned this too, in terms of whether we really need to be optimizing a lower bound. My guess is that it depends on the domain and the amount of risk that that domain is willing to take. I think in some scenarios, probably good lower bounds or some sort of assurances are really important. Now, whether all doctors are familiar with Q values seems quite unlikely, but some sort of, maybe perturbation analysis, or Susan Shortreed and Susan Murphy and Joelle Pinot have some work on this before, sort of looking at how much can you perturb the policy, different interpretability to try to understand for doctors or other sort of domain experts to understand how stable these methods are. Those I think might be really important for being able to deploy them rather than strictly lower bounds on a particular reward function. But I do think probably some assurances on the likelihood of success and the extent of success is probably pretty important, because if it's only a very small improvement, it might not be worth a change or the risk compared to if there's a very large potential gain, either in cost or in terms of outcomes.
Yeah, my opinion is that the focus on off-policy evaluation specifically has been a bit of an over-focus in terms of sort of what we want to do with this down the line. Like in my experience in simulated robotics and a lot of recommendation systems, what we really want is just some sort of off-policy selection algorithm. We don't care much about what the value is. It's just that we have a bunch of hyperparameters and we run about a bunch of jobs, and now we can only run a few on the robots, and which ones are we going to choose? On the other hand, maybe in health and education domains, like Emma mentioned, interpretability is more important than knowing what is the exact value this policy is going to get. What's more important is why is it doing what it's doing, and is there some way to get the client to have confidence in the model, as opposed to just saying, well, we did a bunch of these low bounds analysis and we think it'll be likely about this value.
I think that there's also another element here, which is that if you're doing policy optimization, while you could have evaluation as an inner loop, because you get to pick the policy, that can make the evaluation problem much, much easier. So asking to evaluate some arbitrary policy could be essentially impossible. But if you get to pick the policy, then you could essentially play this game where you find the best policy for which you can confidently say that it's good. And that's probably a much easier evaluation problem in many ways.
I want to also resonate a lot with what Ophir just said, right? So if you think about like supervised learning, what we do, right? Training, validation, and test. And so far, I think a lot of times all we have been talking about is only evaluation for testing, we're learning for training. But we have like ignored a lot about like the problem of validation itself. And presumably like when you do OPE, one of the purposes is like for testing, but another application is that it can help you to do validation, like cross-validation, hyperparameter tuning, model selection, so on and so forth. But now like sometimes you need to just like think about it, like OPE is just one way of doing it. Like you could have like attacked the problem of model selection like directly. And this is related to like, this very recent result, which Emma have mentioned a couple of times, like in the talks and Simon's, like it turns out that under certain scenarios, like doing cross-validation like directly with like Q values is in some sense much simpler and gives you way stronger guarantees than just our policy evaluate each policy and then pick the best. So I think we should like maybe think in terms of like what we want those methods to do instead of like just focusing on, improving those methods themselves.
Yeah, and also if I may, the policy evaluation problem is important in the sense that if you think of the connection to causal effect estimation, it's essentially the same problem. And we know that in statistics and all the supply domains, causal effect estimation is one of the core problems. So you can solve a policy RL or policy evaluation from observational data well enough, then I think that will also have a lot of impact on other apply domains and apply statistics.
I think my question is in some senses, what if we can't solve OPE, Li Hong? Should we look for things? I like Nan's point, right? What if it's really, really hard to solve OPE? Maybe we're just making things harder for us.
And especially that now that Li Hong brought up the causal inference component is, I'm sort of a little bit pessimistic in that causal inference itself, like just for one step, right, is already like a ridiculously hard problem, and there's a whole area like devoted to it, and then we're adding like multi-steps plus the cursive horizon to it. I don't know like how. I don't know how optimistic everyone else is about this. Yeah.
Well, in the one-step problem, if we don't have an observer confounders, I think the problem is relatively easy to solve. I guess a lot of the headaches comes from the hidden variables, so that we have to use all kind of assumptions to do causal inference. But if we are making a Markovian assumption, which is analog in the RL scenario, I think a lot of things can be done, although it's not trivial. But if we are having an observed confounder, then I agree that this is really a very intimidating problem to look at. But I know people are starting to look at this problem.
There was a nice tutorial this summer from Elias Barenbaum about sort of causal RL at ICML, where he's one of the people that's really thinking about this area, as I'm sure many of the panelists know.
Right.
Actually, I'm pretty optimistic about OPE. I mean, in the sense that I think there's been a lot of work over the last 4 to 5 years. There's also some really cool work from Nathan Callis's group that takes more of sort of an econometrics type approach and very doubly robust. I think that we're starting to have pretty good theory for this setting. I think we could do a little bit more on sort of better empirical results, but I think we're getting pretty close on that side. But I think that we're not yet. I think there's still more open questions on the optimization side. I did just want to mention that I think in terms of whether we need it, one paper I found really interesting on this front recently was some work by Akshay and me and others, which was looking at whether you could sort of do model selection. And one of the really cool ideas in that paper, it was an ICML paper, is to say that maybe you'd be able to select, but you wouldn't actually know exactly how good that bound was. So you wouldn't be able to get a lower bound, but sort of provably it would still be the best you could do. And they have this nice trick about assuming this sort of monotonicity in terms of the bias across your different estimators. So I think that's a really interesting question about whether in some cases, even provably, you might be able to do the best when you're selecting among a set of policies or a set of estimators, but you wouldn't be able to know exactly what that value is. And so maybe in those cases, that would also be a satisfying answer to this question.
maybe one thing I might add also in regard to this, like, there's this notion, which I think you guys were getting at, that basically OPE sort of looks like a problem that requires answering counterfactuals, which due to a whole host of causality reasons might be essentially impossible from observational data. But I think one very important detail is that if we are concerned with optimization, it's okay to answer, I don't know. So the really bad thing is to say, I know the answer and this is great, when in fact this is not great. But if you have a system that can say, I don't know, that is probably actually enough to do very effective policy learning. And that might actually be kind of the, the secret that makes us all manageable and not sort of causality complete, so to speak.
I have a small comment or question, or I don't know how to phrase that, but maybe I have some issue with this kind of thinking, because I think that we're often forgetting that we're putting a lot of assumptions in anything that we do. So no matter what, like you can't get causality from nothing. You put causality into the model in some way, this way or another way, and there is no free lunch here. So just saying nothing or just returning the answer, I don't know. If we are frank to ourselves, we should always do that, right? Because we have no idea about how the data was really generated in a complicated scenario and whatnot. So all of the results are going to be qualified where you want to have some, result that provides some sort of guarantees. They're going to be qualified with some assumptions, and then the discussion should be about whether those assumptions are reasonable or not. But at the same time, I agree with that, like enriching the things that you can return, like saying I don't know, or like resorting to some standard behavior, for example. So changing the problem may actually be a good direction to go into. Just wanted to kind of like clarify a little bit about this. Oh, thank you.
You're muted, thank you.
Yeah, it doesn't look like you're muted, but we can't hear you.
No, I think it's his mic has some problem.
You cannot hear me?
Oh, it's fine now.
Oh, okay, good. So I guess I think this uncertainty classification just drive me crazy. So so I think I know Li Hong. I've read the quick paper, very carefully, and I was trying to extend it to nonlinear models in the last few months, and it was pretty difficult. So you got into the same problem as in nonlinear deep reinforcement learning. So just when you have nonlinear neural networks, it's very hard to do uncertainty classification. So that to me, that's at least the main question I couldn't resolve. Like I don't know how to do uncertainty classification for deep models. So and not for the dynamics, not for the Q functions, so on and so forth. So that seems to be one of the major questions that we are facing, which is not necessarily an RL question. That makes it a bit kind of like annoying, because you have to go to the uncertainty classification literature and see what are there, and they are not that much there, I think, especially for out of domain uncertainty classification. So probably that's an open direction that deserves a little more attention, only in my opinion.
Yeah, the two kinds of uncertainty, perhaps what you're thinking is the approximation error type of uncertainty, as opposed to statistical uncertainty. Is that? Oh no,
I'm referring to the statistical one. So you assume that you have you have realizability, let's say, but you just have a domain shift, right? So for example, you learn your dynamics on some data, and then you test on some data point that is not from the same distribution. Then what's the uncertainty for your prediction? So, and for linear model, you can do that pretty well. That's just involve something like X measured under some norm, and that's the uncertainty quantification measure. And for nonlinear models, we don't know how to do it.
Wait a bit. Won't a simple covering argument just give you this?
Sorry?
I mean, like maybe you're not happy with the covering argument. Maybe what you're saying is that, yeah, we do have some tools, but you're not really happy with the tools.
The covering argument, I'm not sure The halving argument. So what argument?
Covering, like using metric entropy and whatnot.
Maybe I'm just missing something obvious here.
About it. But
I
think
think I'm not even exactly sure what it is.
For nonlinear models, uncertainty, they are fairly general, and maybe that's a problem with them, that they're going to be super conservative because of that. I totally agree that we don't have good tools.
One of the way to do it is the Eruda dimension, which sorry, I didn't know what you were referring to, but Eruda dimension is another alternative, but that's also very conservative. So you are requiring that any two models needs to agree on your new example, so that you can be certain about it. And that sounds just a way too conservative.
Tenyu, are you more I would be more optimistic that we'll be able to get them first for dynamics models compared to Q functions. But what is your thoughts, or others too? I mean, I generally feel like it's more likely we can get good uncertainty quantification first in the models rather than all the way across the Q set.
Yeah, I agree. Yeah, I think for dynamics it's easier, but that becomes a supervised learning problem. It's not like RL. So I think that's the catch. Yeah.
Oh, by the way, like let's talk about another catch there. So even for dynamics, if you really have correlated data, I think that you're doomed with your uncertainty quantification again, because you have no idea about the mixing times. And without knowing the mixing times, you won't get nothing. And to estimate mixing times from data from a single pass, we know that that is like, I mean, it is something you can try to do, but without assuming any extra structure, there's no luck there. Yeah.
So I'm just gonna jump in here.
Yeah.
So Scott Neekum, I think, is trying to say something. Scott, if you can unmute.
Oh, I did have a question, although I guess it goes back to OPE. So I don't want to take us too far off, but I guess it's a question nominally for Sergey, but I'd be interested to hear what other people think too. So Sergey had mentioned before that one way of kind of making OPE easier is thinking intelligently about selecting policies that we actually want to evaluate. So maybe looking for the best policy that we can confidently say something about. So I just wondered if, because there hasn't been a ton of work in this area, if Sergey or anyone else has ideas about what the right way to do that kind of search or proposal of policies is.
Well, I actually think that a lot of the work that was discussed in the morning session does basically get at this point, although albeit somewhat indirectly, where if you are pessimistic in some way in evaluating your policy, for instance, with the method that Ting Yu described or the method I described in my talk, it is kind of having this effect of punting on the stuff that you can't evaluate. So if you sort of assign a very low value to things that you're not sure about, that's kind of the same as saying that you don't know, because your policy just won't go there. So in effect, you're just saying, if you don't know what's going to happen, just don't, basically. And that's a decent rule of thumb. And I think these methods are, they're not exactly doing this, but I think they're kind of actually going in that direction. And we might see further evolution on these ideas as leading to that outcome.
Yeah, fair. Thanks.
So to follow up on that a little bit, if we think about this more iterative method that we were discussing before, how do you differentiate between actual low value and don't know value if you were to, for instance, use whatever Q function you learned to inform future data gathering?
Maybe I'll take on that question and also combine it with some comments Chava made earlier and turn that into a new question for Emma. So I think in general, like for example, if we think about the duality methods that Ophir was talking about, or in general this marginalized importance sampling methods, I think the answer is in general you don't know, unless you have some strong assumptions on your function approximator, which goes somewhat back to Chava's point, right? And one comparison I always would like to make in terms of our current status of OPE is to compare how you can do testing in supervised learning, right? How much data does it take to do testing in supervised learning? like O1, right? Or O like 1/epsilon square, something like that. How much data does it take for now if I want to do something like marginalized importance sampling? Well, if you use a neural net, I'm solving another deep learning problem on my test set. Like that would, you mean, in order to satisfy the like realizability assumptions required by my theory, right? So on the other hand, there's this good old, sequential importance sampling that gets rid of this issue, but really it can only evaluate policies that are extremely close to your behavior policy. But I mean, like Ofer, Li Hong, I have been sort of like all in to this MIS regime where I think Emma is still like looking at IS. I'm somewhat like kind of swing back and forth between these, and I would like to hear Emma's thought on like the choices between these two and also everyone else.
I guess I'll say two things. It's interesting that both the method I presented today and our paper on sort of policy gradient from last summer, both are MIS, so they're both doing sort of stationary importance sampling methods. They do rely on the domain, and the representation one has been Markov. And I think that in reality, for a lot of cases, at least some of the healthcare data that we've looked at, I don't think we're using representations yet which satisfy that. So I think that's a big limitation, because I think we're almost definitely getting into misspecification. Maybe in terms of in general, which of the two are more promising, I think partly it depends how well we can estimate those stationary distributions, assuming we're willing to make the Markov assumption. But also to go to Pablo's previous question, I think in the method, like the method that I described today, which is sort of a model-free analog to MOPO and to Morel, all three of these methods maintain a direct estimate of sort of what things are considered to be close or far. Some of them are more soft, but some of them present you essentially a hard label of, an indicator of are you above this threshold or not. So at least you'd have a labeling of every state action pair, which is unknown. And I think that would help a little bit in terms of trying to quantify, is it unknown or is it bad? Because you could use that information for later or build sort of some approximation of the space in which it is unknown. But going forward, I think it's a really interesting question, which of these types of approaches is going to be most effective. I do just want to mention that Nathan Callis has some really nice work with Masatoshi and showing that if you're willing to make the Markov assumption, you're just sort of provably much more efficient, which maybe isn't a surprise, but it's nice to see the gap between IS methods and stationary IS, and you really do get a substantial gain if you can make the Markov assumption.
All right, thank you. So we're a little over time. I think we can go a little more. I just wanted to ask one higher level question, and maybe trying to bring things back into what Emma was saying, that offline RL perhaps is one of the most promising avenues for trying to bring RL into the real world, where we're able to access data that people have been gathering without perhaps RL in mind, and provide new guidance, provide some type of evaluation, or perhaps new policies for them to implement. And what I'm wondering is, say somebody has some data or is able to acquire data, what can we as the RL community give as insights or best practices in terms of gathering this data, so that down the road it will be more amenable to these types of methods, if any?
I think one of the things I would say is if you can record the probabilities of taking the actions under the states, that's not always, probably in many web companies it's logged, but it's not always logged. And we're actually doing some new criminal justice work where we're like, we have to log this, we have to log sort of the probability of sending out text messages and stuff, because often for different subpopulations, you'll have different probabilities, and trying to infer it later leads to all sorts of errors and estimations, and in many cases we really do know it. And so if you do know it and you have access to all the variables that are used to make those decisions, so we can avoid the confounding problem, I think that's huge in terms of us being able to make reliable inferences later.
Maybe this is a little bit of a non-answer, but to turn this around a bit, maybe something I might say is I think we as the reinforced learning community really need to work hard towards methods that don't place any constraints or restrictions. For the simple reason that essentially the fewer considerations you have to have in mind when collecting your data, the more your method will be able to use lots of data. And the one thing we've seen again and again is that if you have a method that can use lots of data, then it will generally work much better. So the more unstructured, the more open world, the more you can grab stuff from the net, the better the thing is going to be. So this is definitely a huge issue right now, but I think it's something we can make progress towards. I think it's really important to take that seriously. It's easy to kind of ignore that when we're working on, like, you know, kind of benchmark problems, as we all do, but we need to really be thinking about that more, I think.
Yeah, I guess for me, I also think of this kind of like offline data as more kind of like somebody give you and you just receive it passively. Because if you are able to kind of like guide them how to collect the data, then why not just run online RL, right? So of course, there could be some situations that you still want to do it in smaller number of runs. I think somebody call it deployment time or something like that, right? So you want to do the collection data in phases, you know, in fewer number of phases. But I guess it's less clear to me why you don't want to do online RL if you can already tell somebody to collect data in some special way.
Well, so I'm thinking in particular for the cases that Emma was saying with health, for instance, right? Where it's not easy to just go and run your RL algorithm on people. But if you can give guidelines to the health practitioners in terms of how they collect data and what type of data they collect, and perhaps what types of strategies they use for their patients. I know Joël Pinot had some work about a decade ago on depression and the sequence of treatments given to patients. And that was dealing with offline data, but they were starting to try to provide guidance to the practitioners into what types of sequences of treatments would lead to better insights into future policies.
But these treatments are on the patients.
Yes.
You have to change the treatment that the doctor originally gave to them.
Well, so for new patients, right? So they have a particular, in this example, they have a particular test that sort of places them in some type of characteristic for the type of problem they're facing. And based on that, the practitioners have a strategy for prescribing medicine. And the point of this work was to suggest perhaps this is not the right sequence that would maximize success and or maximize the amount of information you can gather from this data.
I see. So I guess you're saying that you want to not just to try an arbitrary policy, learn from the RL, but you try some policy that is kind of a mixture of the human policy with a little bit of perturbation, maybe diversity or something like that, so that
Well, yes. I mean, so how can we help the non-RL people help us get the right data so that then we can help them back again with better policies?
I might have to say something about this. The question is how to collect data, but the initial data is something, but when you produce a policy, you will want to gather new data on this. And I'm thinking, for example, about medicine, but there are other application domains where it would be true. The thing is that you want to apply a reinforcement learning policy on real human, on patients. But it will be more like a kind of help for the doctor. And the doctor can give feedback on the decision provided by the policy. And this human feedback can be very useful for training a new algorithm. And it can provide some information. It's not easily quantified, but the human feedback can be very, very important. And this is this loop between the machine and the human that we should also try to extract somehow to provide maybe the next policy.
Yeah, I think that's a really great point. And there's a lot of work, not necessarily in RL, a little bit in RL, but of this human in the loop learning, which I think will become more and more pressing as we start trying to deploy these methods in the real world and with affecting humans in real ways. So perhaps that's a good way to transition into the Gather Town, where we can continue these interesting discussions. I believe the link should be available to all of you, and I think it was, yes, the Simons Institute just put the link. So we will regather in Gather Town. Thank you, everyone, the speakers in particular, for their interesting talks. And thank you, everyone, for the questions and thought-inspiring discussions. See you soon.
Thank you, Pablo. Thank you all.
See you.
Goodbye.
Yep. Thank you. Bye. Thanks.